Hello, welcome back. This is the part two of the lesson Statistical Inequalities. In this lesson, now we are going to look at Cauchy inequality. So, Cauchy inequality says that for any random variables x and y with finite second moments, expected value of x times y whole thing square is less than or equal to expected value of x square times expected value of y square. And the equality holds if and only if y is equal to uh, alpha times x for some alpha constant with probability 1. So this you can see that it involves the expected values and two random variables. Whereas in part one we discussed uh, an inequality with one variable. It also was concerned about the expected value. That was Jensen's inequality. So here this sometimes people write down this quantity, expected value of xy square as e square xy also. But here I have corrected them in mm, some books. You will see that it is written like this. Right. So we will see how to prove this Cauchy's inequality. So in order to prove this, we consider a new quantity called Z. So define Z as y minus alpha times x, where alpha is a real value, real constant. Then you can see that expected value of Z square, right? If you first consider the Z square is going to be y square plus alpha square x square minus twice alpha times x times y. So then when you take the expected value of z square, you are going to get expected value of y square minus 2 times alpha expected value of x times y plus alpha square times expected value of x square. Now, notice that this right-hand side here, I can write down as a function of alpha, right? Actually, it's a quadratic function of alpha. If I call this part A, this part here negative 2 times expected value of xy as B and this quantity as C, then I can write down expected value of Z square is equal to A alpha square plus B alpha plus C. So it's in a quadratic form. Now, in order to derive the inequality, we will observe that uh, if expected value of x square is equal to 0, that means that will imply that x equal to 0 with probability 1, right? Because x square is always greater than or equal to 0. So therefore, expected value of x square equal to 0 will imply that x equal to 0 with probability 1. And in that case, if that is the case, then the inequality will be uh, followed trivially because in that case, this part will be 0. And because x is equal to 0 with probability 1, expected value of y will also be 0. So we will have 0 less than or equal to 0, where, of course, equality prevails in that case. So that is a trivial case. If expected value of x square or expected value of y square is equal to 0, the inequality is immediately true. So what you have to show is now if expected value of x square is not equal to 0, then what can happen is it's greater than 0. It can never be less than 0 because x square is positive. So the expected value of a positive random variable, of course, x square is positive or 0. Now we have considered the 0 case. So if x square is positive, then expected value of x square is always positive. Right. Now also z square that we defined here, z square. Z is a random variable, so therefore z square is always greater than or equal to 0. Uh, Therefore, expected value of z square should also be greater than or equal to 0. Right. For every real value of alpha, right? Because z square is a function of alpha here, right? So whatever the value of alpha, expected value of z square uh, is equal to this function. So that must be greater than or equal to 0 for any value of alpha. So therefore the quadratic function here this function a alpha square plus b alpha plus c function should be greater than or equal to 0. That means it's non-negative for all real values of alpha. Right. So what you will have is a function like let me just draw it. Notice that here expected value of a is greater than 0 because a is equal to expected value of x square. Now we are considering the case where expected value of x square is positive. So this constant is positive. In that case, when you have a quadratic equation with a positive constant term at the coefficient of x, the variable, you know that the quadratic function has a minimum, right? So now, therefore, what you are looking at is expected value of z square greater than or equal to 0 means this thing is greater than or equal to 0. So therefore, what you have is something like this. Let me try to draw a sketch, right? So if this is alpha, so this is this whole thing a alpha square plus b alpha plus c. So the either the function is uh, completely above this axis, or it might even be something like this, touching at this point greater than or equal. Right. So if you have this situation or this situation, right? Of course, if you have this situation, then the discriminant, which is the b square minus 4 times AC, should be negative because this doesn't cut the x-axis. There are no roots for the equation coming from this. So therefore, in that case, the discriminant of this function should be negative. If you have this situation, then the discriminant will be equal to 0, giving you only one root for the equation that you get by equating this to 0. Right. So therefore, if Ez square is greater than or equal to 0, this function is greater than or equal to 0. Therefore, you have either this situation or this situation. So therefore, the discriminant must be less than or equal to 0. Right. If you have discriminant greater than 0, then you should have something like this, two roots, right? So then the function will be negative in some part. Therefore, that will be a contradiction. So therefore, if Ez square greater than or equal to 0, this is greater than or equal to 0, that implies that b square minus 4ac should be less than or equal to 0. So if you put the values for b and a and c, you will get the following expression here. Okay, before that, I will delete this. So substituting for A and B and C, we get this expression. This is what you get when you substitute for A, B, and C, where A is equal to expected value x square, B is equal to this quantity, and C is equal to this quantity. So when you simplify this, you get finally expected value of xy square less than or equal to expected value x square times expected value of y square. That is the inequality in the Cauchy's inequality. But there's a part we have to prove, that is equality holds if and only if y is equal to alpha times x for some alpha, right? So that means y should be a constant multiplication of x. That is the only case where this expected value of x times y square is equal to expected value of x square times expected value of y square. So in order to prove that, notice that this thing will be equal if the equality happens in this equation, right? So that means the discriminant is equal to 0. If the discriminant is equal to 0, as I shown you earlier in the picture, there will be only one root uh, where that function will be equal to 0. That means in that point, expected value of z square, where that is actually our function, right? A alpha square plus b alpha plus c is equal to z square. So if you equate to that 0, you get an equation. So that equation will have one root, right? So therefore, z square will be equal to 0 at some single value of alpha. Now, at that point, since z square is greater than or equal to 0 random variable, expected value of z square will be equal to 0 if and only if z square is equal to 0 with probability 1, right? Since z square is greater than or equal to 0, expected value of z square will be equal to 0 if and only if z square, the random variable itself, is equal to 0 with probability 1. Right? Therefore, z is equal to 0 with probability 1. Right? That is, y is equal to alpha x with probability 1, because we defined uh, z to be y minus alpha x. So if this is equal to 0 with probability 1, y is equal to alpha times x with probability 1. So that means the equality in the Cauchy's inequality uh, holds if and only if y is a constant multiplication of x. So that is the proof of the Cauchy inequality. Right. Now we will look at few other things connected to that. Actually, these are the more important things, practically useful things coming out of the Cauchy inequality. The first thing I am mentioning is, sometimes in some books, Cauchy's inequality is mentioned as Cauchy-Schwarz inequality. Right. So Cauchy equality and Cauchy-Schwarz inequality are the same. And another important thing about it is, actually, is here you have in general expected value of xy square is less than or equal to expected value of x square times expected value of y square. But this x can be some function of some other variable as well. And also y can be some function of some other variable. And therefore, we can actually consider more general situation like this: expected value of, right? Or so for example, what you have here, they are x. You can write down, instead of that, you can write down, for example, say u may be some function of x, right? So you may have, for example, for two random variables u and v, expected value of u times, I will omit v because usually we take v for the variance. So I'll take u and w, for example. So if u and w are two random variables, you are able to write down something like this. Cauchy's inequality will be right for u and w like this: u w whole thing square less than or equal to expected value of u square times expected value of w square, right? But this u can be some function of x. This w can be some function of y, right? And therefore, this u square is equal to fx square, which is usually written as f square x. This w square is the square of gy, which is also written as g square y. So therefore, because Jensen's inequality, Cauchy's inequality will be correct for any two random variables with finite second moments, right? If u and w are two random variables like this, you can write down like this. But this u itself can be a function of x, and w itself can be a function of y. Therefore, in general, you can write down a more general Cauchy's inequality in this form. Right. In particular, for example, if you take gy to be equal to 1, you will have this expression, expected value of fx. In that case, you will first of all have fx, expected value of fx square less than or equal to uh, expected value of uh, f square x. This part will be 1 in that case, right? But when you take the square root, this side will be, you have to consider the absolute value because you are considering only the positive square root, less than or equal to the square root of expected value of f square x. Right, so that is another special case when gy is equal to 1. Another special case is you can take fx to be x minus mu x, right? So that means capital X minus the expected value of x. And you can take gy to be y minus gy, gy to be y minus the mean of y, that is mu y. So in that case, the expression will be like this: expected value of x minus mu x times y minus mu x whole thing square less than or equal to expected value of x minus mu x square, which is the variance of x, time the expected value of y minus mu y square, which is the variance of y. Right. So here mu x is the expected value of x, mu y is the expected value of y, and sigma square x is the variance of x, that is the expected value of x minus mu x square. And sigma square y is the expected value of y minus mu y square. Right. So this term here, this one here is the expected value of x minus mu x square. So that is the variance of x, and similarly for y. Okay, now so what we have here is actually from this one we can get some expression for the covariance, because this is actually expected value of x minus mu x times y minus mu y. This part is the covariance between x and y. So what you have here is the square of the covariance, and less than or equal to variance of x times variance of y. So therefore, you can say covariance square of x between x and y, right? Is the square of the covariance between x and y less than or equal to variance x times variance of y. Right. Now, if you divide the whole thing by variance uh, of x times variance of y, you will have covariance square between x and y divided by variance of x times variance of y less than or equal to 1. If you take the square root of that, you will have covariance between x and y divided by the standard deviation of x times the standard deviation of y. Is going to be between -1 and +1, right? If the square is less than or equal to +1, square root is going to be between -1 and +1, inclusive those two, right? So let me write down that to be a little bit clear, more clear here. So you will have covariance between x and y divided by uh, standard deviation of x times standard deviation of y, right? After taking the square root, is going to be between -1 and +1. Now, this quantity is called the correlation. There's the correlation, or sometimes write down just core between x and y. So it tells you that the correlation between x and y is a number between -1 and +1. So that's coming from this also. You can prove that using this. There are other ways to prove that, but you can also show that the correlation between two random variables is going to be in a number between -1 and +1, inclusive those two, using the Cauchy's inequality. So in that case, the equality will prevail. As you know, equality will prevail if the one variable that you consider y variable that you considered is alpha times another variable. So in this case, the variable, two variables that we considered was x minus mu x and y minus mu y, right? So therefore, y minus mu y should be equal to some constant times x minus mu x. That is the situation where uh, equality prevails here. So therefore, in this case, we can say no, in the inequality, equality prevails if and only if y minus mu y is equal to some constant times x minus mu x, where the constant is written as beta here, right? So if you have this kind of situation, relationship, actually this means y is equal to some beta x plus some other constant, right? So that means if y and x are mathematically linearly related, right? That is the situation where the correlation between x and y can be either +1 or -1. It will be +1 if the coefficient of x is negative. Otherwise, it will be positive, right? So that is all about uh, the Cauchy's inequality. Next, we will look at another important inequality called Chebyshev's inequality. Right. So the previous two inequalities were about expected value. Jensen's inequality was about expected value of a single random variable. Cauchy's inequality was about the expected value of two random variables. The Chebyshev inequality is about a probability of a random variable. So it concerns the probability distribution actually. It doesn't really concern the probability distribution, whether it's normal laws, gamma or exponential. It's a general inequality, but regarding the probability. Right. So Chebyshev inequality provides an upper bound for the probability of being outside the interval around the mean of on the scale of a standard deviation of a random variable x. So it's going to tell you it's going to give you an upper bound. The probability that x minus mu is greater than or equal to some given value is less than or equal to some value. So that value is going to be given by the this inequality, Chebyshev's inequality, right? One important thing is that this Chebyshev inequality is valid for any distribution. So it's actually distribution free inequality as long as uh, they have finite mean and finite variance or finite standard deviation. If the random variable has finite mean and finite standard deviation, regardless of the actual distribution, this inequality will be valid. So it's going to be kind of a conservative inequality, right? If you consider a particular distribution, you may be able to get a better inequality. So, but anyway, this is also true, but it's going to be a conservative inequality, valid for any random variable as long as it has a finite mean or finite variance. So let's look at that mathematically, Chebyshev's inequality. Let x be a random variable. Let the random variable x have mean mu and standard deviation sigma. So when we say it has these two, that means they exist, right? Then for every positive k, the probability that x minus k absolute value greater than or equal to k times sigma is less than or equal to 1 over k square. So that is what the Chebyshev's inequality says, right? So the probability that x will be beyond uh, k times sigma from the mu, from the value of the mean, is going to be less than or equal to 1 over k square, right? So in other words, more useful will be to say what is the probability, what can you say about the probability that x will be x will be around mu and within k times sigma distance from the mu, right? What can we say about that? What actually from this one we can say probability x minus mu absolute value less than k times sigma is greater than or equal to 1 minus 1 over k square, right? So that's coming from taking the complement, right? So this tells you, what does this tell you? This tells you that the random variable, most of the values actually, right, will be within k times sigma distance from mu, and that probability will be greater than or equal to this quantity. And you can see that when k increases, of course, this quantity will decrease. Therefore, the probability will be getting more and more close to 1, right? Okay, so that's what the Chebyshev's inequality gives you, and this is a very useful inequality to get some idea about any random variable, the distribution of any random variable, how the values of x are going to be distributed around mu, right? Okay, so let's try to prove this theorem. I'm going to consider here uh, uh, the proof for the continuous random variable. You can consider the same idea for a discrete random variable. In that case, instead of these integrations, there will be summations. So let's consider the probability that x minus mu greater than or equal to k times sigma, where k is a constant, positive constant, right? The probability that x minus mu greater than or equal to k times sigma can be obtained by integrating the density function of x uh, in the region of x where x minus mu greater than or equal to k times sigma. So this will be usually the union of two uh, intervals. One interval will be x greater than or equal to mu plus k sigma. The other interval will be the interval where the x is less than or equal to mu minus k times sigma. So this will be therefore the union of those two areas, right? So if I consider, for example, uh, a real line, suppose this is the mu value, that is the expected value of x. So x minus mu greater than or equal to k sigma is going to be something like this. So if this distance is k times sigma, this interval here from this point to infinity or whatever, if it is going only up to a certain b value, that part, or it might be up to positive infinity. And then if this distance is again k times sigma, what you're looking at is this interval again from minus infinity or some value from a to this point, right? So this thing is the union of this interval and this interval. Right? So you are integrating the density over that union of those intervals. And this probability will be equal to integrating the density over this and this, the summation. So you can write down that as the integration of fx on this region plus the integration of fx on this region, right? So on this region, that is x in the region x minus mu greater than or equal to sigma, we know that x minus mu square is going to be greater than or equal to k square times sigma square. So therefore, if you divide this by this quantity, you can say this quantity is greater than or equal to 1 whenever x minus mu is greater than or equal to k times sigma, right? So therefore, I can now build up inequality. If I multiply this quantity by this quantity, then the integration will give me this inequality. So first of all, we have already this one. This probability is equal to this one, but that will be less than or equal to this quantity times fx dx integrated over this region, because this quantity is less than or equal to 1 on this region. Right. Therefore, the probability of x minus mu greater than or equal to k times sigma is less than or equal to this quantity. You can take this 1 over k times sigma square out of the integration. So you can see that this integrand here is, this one is greater than or equal to 0. This is always greater than or equal to 0. Therefore, the integrand is non-negative. So therefore, this thing will be even less than or equal to the integration of this thing over the whole real line, right? So this thing will be this part, if you consider this part only, that will be less than or equal to the integration of this quantity from minus infinity to plus infinity. So that's what you have here. Therefore, you can get an inequality for the whole thing like this, right? So the probability of the left hand side, probability x minus mu greater than or equal to sigma less than or equal to 1 over k square sigma square time the integration from minus infinity to plus infinity x minus mu square fx dx. But integration from minus infinity to plus infinity expected value of x minus mu square fx dx is actually the same as expected value of x minus mu square, which is the same as variance of x, and that is the same as sigma square. So therefore, so this part is sigma square. Therefore, you will have this thing is less than or equal to 1 over k square sigma square times sigma square, which is equal to 1 over k square. So that's what the Chebyshev's inequality is, right? So the probability x minus mu greater than or equal to k times sigma is less than or equal to 1 over k square. And you can write down equivalently, you can say probability x minus mu less than or equal to 1 over, less than or equal to k times sigma is greater than or equal to 1 minus 1 over k square. Right. So that's a very useful result actually to get a general idea about how the values of possible values of a random variable are distributed, regardless of the name of the distribution. Actually, generally, the distribution of a real random variable doesn't have a name. But usually we use the models for those things. Those have names. So whatever the distribution of the random variable x, as long as the mean is finite and variance is finite, then the possible values will be distributed around the mean according to this criteria, right? So, for example, if you take k to be 2, then the probability x minus mu less than or equal to 2 sigma is greater than or equal to 1 over 1 minus 1 over 2 square. So that will be 1 over 4. So therefore, this side will be 0.75. right? So that means for any random variable with finite mean and finite variance, the values of x will be within two standard deviations from the mean with at least 0.75 probability, at least. And if you put k equal to 3, therefore it will have 1 over 1 minus 9, 1 minus 1 minus 1 over 9. So that means 8 over 9, right? So the probability that uh, the possible values of x within three standard deviations from the mean is greater than or equal to 8 over 9, right? So like that. So let us now apply this Chebyshev inequality for some particular distributions and actually show that uh, the inequality is true, and actually it's a very conservative inequality, right? So for example, let us consider a normal distribution with some mean and some variance. In this case, doesn't matter actually what the actual value of mu and what actual value of sigma is. You can show that whatever the mu and sigma, if you consider k equal to 2, the actual probability that x minus mu less than or equal, you can say equal to also because x is continuous here, less than or equal to 2 sigma, you can find out this probability knowing that x has a mean mu and variance sigma square is going to be around 0.9545, approximately 0.95. Right. And similarly, if you put k equal to 2.5, you will see it's equal to this probability. Theoretically, we can find out these ones. K equal to 3 is that the probability that the x is within three standard deviations of the mean is going to be 0.997 approximately. So with these are actually well-known results for the normal distribution. This one, and if you put k equal to 1, we know 68%, approximately 68% of the observations are going to be within one standard deviation from the mean. So that's what we usually call the empirical rule. But if you apply the Chebyshev's inequality, what should be the value? What is the value? It says that the probability that x will be within, say, two standard deviation is greater than or equal to 0.75. That is correct because we have 0.95, so greater than. But what the Chebyshev's inequality tells us is that it's greater than 0.75, which is correct, but this is a very conservative lower bound in that case. And for example, if you put k equal to 3, the lower bound given by the Chebyshev's inequality is 0.84. Actual probability is 0.98. So Chebyshev's inequality says that the probability that x minus mu is less than or equal to 2.5 sigma should be greater than or equal to 0.84, and we see that is actually greater than that value. And within three standard deviations, Chebyshev's inequality says that according to, as I mentioned, it could be 8 over 9, greater than or equal to 8.9, 8 over 9, which is 0.8889. And actual probabilities, of course, satisfying that condition, right? It's more than that. It's nearly 1 in that case. If you apply the same thing, right, this is not going to change depend on the distribution. These are the lower bounds for this kind of probabilities, right? A probability x minus mu less than or equal to k times sigma is greater than or equal to these values depending on the value of k, regardless of the distribution. And I have calculated here the corresponding probabilities for an exponential distribution with lambda equal to 1. So these again, you can see that these probabilities satisfy that means greater than or equal to these lower bounds. If you consider, for example, so in this case, the distribution is very skewed, gamma 1. Still, the lower bounds are correct here. And if you consider gamma 2 1 distribution, for example, we can find out the probability that X is within 2 standard deviation, within 3 standard deviation, within 2.5 standard deviation, we can find out theoretical values theoretically. And you can see that these actual probabilities are, of course, greater than the lower bounds given by the Chebyshev's inequality. So here I have looked at the same situation for some discrete distributions, binomial, Poisson, and negative binomial. Still, we can see that the actual probabilities are greater than uh, the lower bounds given by the Chebyshev's inequality. Right. So that is the end of this lesson, part two of the discussion of about important statistical inequalities. So in this these two parts, we discussed uh, three important statistical inequalities. The first one was the Jensen's inequality. The second one was Chebyshev, Cauchy's inequality, and the last one is Chebyshev's inequality. Right. So that is the end of this uh, part of this lesson about the uh, important statistical inequalities.